In this video, we're going to start looking at oxidation-reduction reactions, and I got to admit, I love balancing redox reactions, so this is going to be awesome here. In general, an oxidation-reduction reaction is just one that involves an electron transfer. Now, you may not have used the term redox in first-year chem, but you definitely looked at different types of reactions like synthesis, decomposition, the replacements, combustion. This oxidation-reduction concept is just another way of classifying chemical reactions. Now, something like the synthesis of sodium chloride could also be considered redox. We know that sodium is the electron donor with a +1 charge. Chlorine is the electron acceptor with a -1 charge. So there is an electron transfer involved in the synthesis of sodium chloride. There used to be an old AP question that would say, like, describe 2 ways you could classify this chemical reaction. And we would say it could either be synthesis or we could also call it redox. One of the first things that we need to do in order to get to the fun stuff, the balancing redox, we need to be able to assign oxidation numbers. Now, these oxidation numbers just kind of tell you how the electrons are being transferred. Who's the donor, who's the acceptor. Now, if it's an ionic compound, this isn't an issue. It's the exact same thing as the charge. So this will be ionics, and specifically ionic compounds should be metal plus nonmetal. So if you're having trouble identifying, I don't know if this is ionic or covalent, the ionics will have a metal out in front. Now, often we can find the charge by looking at the periodic table. If it's a transition metal, then we'll find the charge on the negative anion first, and then we'll balance the positive charge on the transition metal afterwards. Now, assigning an oxidation number with a covalent compound is a little bit tricky, only because technically a covalent compound does not involve a transfer of electrons. We're sharing electrons. So a lot of this we'll talk about more when we hit Chapter 8, which is bonding. But some of these terms may be kind of familiar to you. That you may remember this term nonpolar covalent. Nonpolar covalent means that the electrons are being shared equally between 2 atoms. Often this is a diatomic, like, chlorine, fluorine. It could be oxygen, hydrogen, or it could just be 2 atoms that have a really similar electronegativity where they're sharing the electrons equally. In that case, we kind of split the electrons equally between the 2 atoms. So if I had a single bond and I'm sharing 2 electrons, we count 1 electron for each atom. If I had a double bond, which is the sharing of 4 electrons, I count 2 for each atom. And again, some of this we'll hit up more when we do the bonding. Another term that may be familiar to you is this idea of a polar covalent bond. We're sharing the electrons, but we're not sharing equally. Here we're going to have nonmetals. It's covalent. And more specifically, the most important thing to note here is this. The electrons are always held closer to the atom with a higher electronegativity. You might remember that fluorine has the all-time highest electronegativity rating of all the elements. It's a small atom. There's lots of attraction between the nucleus and the electrons. And if you think about the outermost shell, it's got 7 valence electrons. We want 8. So fluorine really wants electrons. So as I go closer to fluorine, like oxygen, sulfur, chlorine, all of those guys also have real high electronegativities. Nitrogen is real high. So if we have a covalent bond and we have to assign these oxidation numbers, and we're having a little trouble deciding, like, should something be positive or negative, the atom with a higher electronegativity has a higher attraction for electrons. So whatever the amount of electrons are in the bond, we assign them all to the atom with a higher electronegativity. So for example, in water, oxygen has a higher electronegativity. We're going to assign those electrons to oxygen. So we kind of assume that oxygen gains an electron from each hydrogen, and we'll assume that each hydrogen loses the electron, even though it's technically not that hydrogen is just giving away his electron. They're just not shared equally. The electrons are held closer to the oxygen. Now, don't let all this bonding kind of get the best of you. Here's what I really want to look at. This chart does a nice job of kind of summarizing how to assign oxidation numbers. Rule number 1, if you have an element, anything in its elemental form, the oxidation number will always be listed as 0. Because technically, if I have like sodium solid, that's just sodium atoms. If they're not in a bond with anything, they're not transferring electrons. So any pure metal would always have an oxidation number of 0. Any noble gas would have an oxidation number of 0. It's not in a bond. If we have diatomics, we're also going to list them as 0, as long as they're in their elemental form. So O2, oxygen, gas. That's its elemental form. Oxygen exists as a gas. We're going to list it as 0. Now, if by chance they had oxygen listed in any other phase, that would open up a new can of worms, and we're probably not going to have to deal with that. Most often, the diatomics will be in their most common phase. So something like hydrogen, H2, nitrogen, oxygen, fluorine, chlorine, those should be listed as diatomic gases. Bromine is a diatomic liquid. Iodine and astatine would be diatomic solids. So in general, anything in the elemental form, 0. Now, if you have an ionic compound, the charges of the ions are the same as the oxidation number. So if I had sodium chloride, I just look at the periodic table, I find the charges, and boom, that's the oxidation number. If I had something with a transition metal, let's say I had, PbO2, then again, I just look at the charge on the negative ion, periodic table, oxidation number of oxygen should be -2. And then I balance the lead. Oxidation number is +4. So in anything ionic, the oxidation number is just the charge. This should be no shocker. Fluorine will always have an oxidation number of -1. Fluorine is always -1. Fluorine has the highest electronegativity of all the elements, so it's going to be negative. And fluorine wants to gain 1 electron. So fluorine will always be -1. Now, sometimes that's not an issue. If I had HF, hydrogen fluoride, I would have guessed that. I would have guessed -1, that's its charge on the periodic table. Hydrogen is +1. Well, look at that. It's the charge on the periodic table. We probably would have gotten that right. But now, here's an interesting one. What about this? Phosphorus trifluoride. Oh. Okay, so this is covalent. Phosphorus and fluorine are both non-metals. Now, they don't have the same electronegativity. Fluorine has a much higher electronegativity. Fluorine is always -1. Now again, it's not that fluorine is gaining an electron, but the electrons in these 3 bonds will be held closer to the fluorine atom. Now this may bother you, but we're going to list phosphorus as +3. Oh no. That just doesn't seem right. That's not the charge of phosphorus on the periodic table. If I look at phosphorus, normally I would assign him a charge of -3. Normally a phosphorus atom has 5 valence electrons. He wants to gain 3. But when we're in a bond like this with fluorine, again, we're kind of looking at how those electrons are being shared. They're being held closer to fluorine. So I would say if you have fluorine in your compound, -1. Assign them a -1 right away. Don't even think about it. And then we'll balance out the charge on the other atom. So this has to be a neutral molecule. Phosphorus must be +3. But just be aware that the oxidation number may not always be the charge on the periodic table. It will if it's ionic. Here's another gimme. Oxygen, -2. List oxygen as -2. Now it does list an exception. In peroxide, the oxygen is actually -1. Each oxygen is -1, which gives me the O2 -2. But that's not very common. So, 99% of the time when you're dealing with oxygen, you're safe right away assigning him an oxidation number of -2. And then again, we'll balance out the rest of the oxidation number depending on if the particle is neutral or if it's a polyatomic, if it's charged. So again, some of this you would probably get right. Oxygen -2. Oh yeah, to make this neutral, each hydrogen is +1. That one ends up being like the periodic table. But again, we should just be aware that this is a covalent compound. I know it looks like I'm putting charges in there, and normally that would indicate a transfer of electrons, ionic. Well, here we're just saying that the electrons will be held closer to the oxygen. He has a higher electronegativity than hydrogen. Carbon dioxide, I'm going to say oxygen's -2, which leaves the carbon as a +4. Awesome. And the other one that's kind of a gimme, hydrogen, give him a +1. He's a small atom, not a very high electronegativity, not likely to gain electrons. So you're always safe going with a +1 when it comes to something like hydrogen. And again, we looked at water. Well, that's what I would have guessed on the periodic table. Chlorine is a -1. I would guess, yeah, hydrogen's a +1. Now if you have something like this, NH3, I'm going to say +1 on the hydrogen, which leaves me a -3 on the nitrogen. So again, like earlier, I've got phosphorus listed as +3. Phosphorus and nitrogen are in the same group. You may find that you're getting different oxidation numbers depending on what those elements are bonded to, and that's okay. Also, we kind of said, like in an ionic compound, it's always positive, negative. Don't freak out here. This isn't ionic, and it's technically not transferring the electron. Nitrogen is not gaining 3 electrons. It's just holding the electrons in the bond closer to himself. So we'll give him the -3 charge. Okay, so let's look at a couple good examples. I promise this isn't that bad. It's actually kind of fun. Often it's what you would have guessed by looking at the periodic table. So we checked out carbon dioxide, CO2. Excellent. Oxygen is always a gimme, -2. So to make this neutral, +4. But now watch what happens. If I had something other than carbon dioxide, let's say I have carbon monoxide. Oh, this is different. I'm going to say -2. I'm going to say +2. And again, don't freak out, because we had said often that carbon's charge could be like a +4, -4. Carbon's kind of in this goofy spot on the periodic table. Well, honestly, 99% of the time, carbon is in a covalent compound. We're not transferring electrons. Carbon's usually sharing the electrons. Now, in this case, it's just going to share the electrons closer to oxygen, who has a higher electronegativity. So again, these aren't always the same thing as the periodic table's charge. Often they are if it's an ionic compound. So don't get your undies in a bundle if you find yourself wanting to list carbon as something other than + or -4. Here's another good one. Sulfur hexafluoride, SF6. Fluorine's a gimme. It's always -1. So to make this neutral, the sulfur is a +6. Oh no, that's not what it says on the periodic table. The charge on sulfur in an ionic compound is normally -2. Sulfur has 6 valence electrons. He wants to gain 2. But this is not ionic. These are 2 nonmetals. They're going to share electrons, but the electrons will be held closer to the 6 fluorines. Now we can do this with polyatomics, which is actually kind of common. Nitrate, NO3 -1. Okay, so whatever I assign for oxidation numbers, they need to add up to an overall -1 charge. Oxygen's always a gimme. He's always -2. There are 3 oxygen, which gives me a -6. I need this to have an overall charge of -1. The nitrogen is +5. Okay, again, I get it. That's not the normal charge on nitrogen. But this isn't ionic. So I think earlier we listed nitrogen as like a -3. Now we're listing him as a +5. That's okay. It depends on if nitrogen's in an ionic or covalent compound. What's he bonded to? Sometimes nitrogen may have the higher electronegativity, like when nitrogen was bonded to hydrogen. Well, then nitrogen does end up with a negative oxidation number. But not in this case. Oxygen has a higher electronegativity. He's closer to fluorine. Now here's kind of another goofball. This thing's not very common, but just in case you ever run into him. Okay, this iron oxide is not the most common form. The most common are probably Fe2O3. There's an FeO. This is ionic. There's a metal. -2 on the oxygen, which means I have a total charge of -6 on the back end. Each iron must be +3. So that would be the oxidation numbers. +3 on the iron, -2 on the oxygen. Do you see what happens with this Fe3O4? I want to go -2 on the oxygen, which gives me a -8. How the heck do you do a +8? +8/3. You can have oxidation numbers that are not whole numbers. Is this very common? No. Will you ever see this? Highly doubt it. But just in case you do, it would be okay to have an oxidation number that is not a whole number.